we're going to take our problem-solving method. So go ahead and title this page of your notes problem-solving method, and then put it into your table of contents. And here's what we're going to do. So I want to start thinking about, we've been thinking about distance, displacement, velocity, speed, acceleration. We've been thinking about those concepts. But I want to start doing real calculations with them, right? So I want to start making it look a little bit more like math than like concepts. And so I'm going to start here by just listing the things, the quantities we've talked about, and then we're going to give them mathematical symbols. So the first pair of well, it wasn't the first, but one pair of concepts we talked about was distance and displacement, right? So remember, distance is the scalar form that has just magnitude, and displacement is a vector form that has magnitude and direction. That means displacement can be negative, but distance cannot. Now, we are going to abbreviate that when we are doing mathematical formulas. We're going to abbreviate that with a lowercase d. And the base unit, the unit that we're always going to use in physics, is we're going to measure our distances in meters. There are other units we could use, but in physics we're going to use meters. The next pair of concepts we talked about were speed and velocity. Again, speed is the scalar, velocity is a vector and includes direction. But for both of those, we're going to use the symbol v. We're going to use the symbol v even when we're talking about speed. And we are always going to make those measurements in meters per second. Next, we're going to have time. And we are going to use time, we're going to use the symbol lowercase t. We're always going to measure that in seconds. And then we're going to have acceleration, which we're going to use lowercase a. And its units, as I very briefly discussed when we were doing the Nearpod, but the units of acceleration are meters per second squared. Okay, let's talk about that for a second because that's a little bit weird. Why are the units of acceleration meters per second squared? Well, to explain that, what we're going to have to do is we're going to have to look at what are the equations for velocity and acceleration. So for the velocity equation that we're going to use, and in this class you do not have to memorize equations. I will always give them to you. But the velocity equation that we are going to use is velocity equals displacement divided by time. That's the velocity equation we're going to use. The acceleration equation we're going to use is going to look a little strange. The equation is acceleration equals delta, that's this triangle, means delta. Acceleration equals delta v divided by t. Okay, what is delta v? So if you've taken chemistry before, you may have seen a delta before. But delta is a mathematical term, that mathematical symbol that means change. So when I say delta v, what I mean is change in velocity, right? So let me explain then why the units of acceleration are meters per second squared. The units of acceleration are meters per second squared because if you take meters per second and plug that in for velocity, and then you take seconds and plug that in for acceleration, you get meters per second, or another way to say that is meters per second squared. Okay, so that's the equation for acceleration. That's why the units for acceleration are going to be meters per second squared. Now I'm going to give you one other equation, and that's the equation for delta v. So whenever we find delta v, we're going to say that delta v is equal to the final velocity, which I'm going to abbreviate as v with a subscript f, minus the initial velocity, which is v subscript I. And if you need to remind yourself that, you might say vf means final velocity, vi means initial velocity. Let me explain why this makes sense, right? If you say that you went from 10 to 15 meters per second, what's the change? Well, if you went from 10 meters per second to 15 meters per second, you would take the final, which is 15, minus the initial, which is 10, which would give you a delta v of 5 meters per second. That makes sense because that's what the change was. All right. So this is just background information, and then I'm going to show you what our problem-solving method is, and then we're going to do a couple example problems that explain, that show how this works, right? Okay. So the method itself, the problem-solving method itself, in physics we're going to use a 5-step problem-solving method, and I'll show you what each of these steps mean in a second. Pardon me. But we're going to start by just writing them down. The first step is going to be to draw a picture. The second step is going to be what I call the knowns and unknowns step. The third step is going to be the choose an equation step. The fourth step is going to be plug and chug. And the fifth step is going to be give me the answer with units. Now, why do we do this problem-solving method? Okay. This is just a consistent way. It keeps you organized, right? But the other thing that's important is when you're showing your work, you're not just showing your work for yourself. You're showing your work so that when I'm looking at it, I understand your thought process. And if you do these things, I can understand your thought process. All right, so let's do an example problem. All right. Here's my example, the first example. And you do not need to write this in your notebook. That's why I printed it, because you don't need to write in your notebook. We're just going to... You're going to write what the solution in your notebook, but you don't have to write the actual question in your notebook. Okay, how long will it take a car traveling 15 meters per second to go 50 kilometers? All right, that's the problem. So if you were given this problem, how would you solve this? Well, let's look at our problem-solving method. So step one is we need to draw a picture. Why do I ask you to draw a picture? I ask you to draw a picture because this is physics class and not math class. Every bit of math that we do is connected to a physical reality, and drawing the picture keeps us connected to the physical reality. So I was starting to draw a bike, but I'm going to draw a car. This is my car, right? So I want to be clear. When I say draw a picture, it doesn't have to be pretty. It just should be clear what it's doing. So here's a car traveling 15 meters per second. So I'm going to draw a velocity vector going forward at 15 meters per second. And then I'm going to say I went 50 kilometers, and I'm going to draw that as just saying, okay, I went this distance. And this is a long distance, but I'm going to say that this distance is 50 kilometers. Okay? That's what I mean by a picture. I have turned these words and these numbers into a physical reality. I've indicated that this thing's a speed. I've indicated that this is the distance. That's the first step to draw a picture. Okay? Second step is to do the knowns and unknowns step. Okay? What do I mean by knowns and unknowns? What I mean is that for every number I'm given, I want to know which of these symbols does it go with, right? So for example, if I see 15 meters per second, what is that? Well, 15 meters per second is a speed. So I'm going to start by saying the speed, or the velocity, is 15 meters per second. That's one of my known values. I got another known value, and that is this. What is 50 kilometers? Well, kilometers is a measure of distance. So my distance is 50 kilometers. And if I want to know how long it will take, that's a time. And so this is what my unknown is. So I say t equals question mark. This is what I mean when I say do my knowns and unknowns. These are the things I know. This is the thing I'm looking for. All right, now there's one thing here, and you'll notice that my distance is in the wrong units because I'm not used to distance being in kilometers. I want my distance to be in meters. So this is where we have to do what we were doing in the last unit. We have to do a conversion. And I will always give you a hint that you have to do a conversion by making the number bold. So I know I got to get from kilometers to meters, and if I look back at my notes, I would see that there are 1,000 meters in 1 kilometer. So this comes out to be 50,000 meters. Okay, where are we at? So I've drawn my picture. I've done my knowns and unknowns. The next step is to choose an equation. Which equation makes sense to use? I've got a v, a d, and a t. Which equation has a v, a d, and a t in it? It's this equation, right? So I'm going to choose that equation. I'm going to write it down. V equals d over t. So that's step 3, is I've chosen an equation. Step 4 is plug and chug. that means I'm going to plug in the numbers where they go. So the 15 goes here where the velocity goes. The distance in meters is going to go on the top, so the 50,000 meters is going to go on the top. And the time, I don't have to put the units. The time, if I don't know it, I'm going to leave it as a symbol. Right, so I'm going to leave it as t, because that's the number I'm solving for. So now I've done the plug and chug step, and I need to solve it. Okay, this is an algebra problem, so you should know how to do this. But just to be clear, the way that I'm going to solve this algebra problem is I've got to get the t by itself. Remember when you got a fraction, the way that you solve this algebraically is you always want to multiply by the thing that's on the bottom of the fraction. And you're going to multiply that on both sides of the equation. So if I multiply both sides of the equation by t, then my times are going to cancel out, and I'm going to be left with, on this side, t times 15 equals 50,000. Now how do I solve that? I divide both sides by 15, and this is where we get out our calculator, and we know that my 15s have canceled out, and I'm going to do 50,000 divided by 15, and we should see that the total time that I take is 3,333.3 seconds, and you can always round. And I know it's seconds because it's time, and that's my answer. But notice I've done all 5 steps. I've done a picture, I've done a knowns and unknowns, and I've chosen an equation, plug and chug, answer with units. All right, that's my first example problem. Let's try another example problem. For this example, I guess I should go a little bit lower on this. So in this example, we're going to have a car traveling at 30 meters per second, and it undergoes an acceleration of 1.2 meters per second squared for 5 seconds. How fast is it going now? Okay, so again, we always start with a picture. So I'm going to draw my car, and the car is traveling at a speed of 30 meters per second at the beginning, so I'm going to draw it going 30 meters per second. It undergoes an acceleration of 1.2 meters per second squared. Remember, the way that I draw an acceleration vector, I talked about this in the last video. The way I draw an acceleration vector is I draw it as a double arrow. So I've got 1.2 meters per second squared is my acceleration. So I'm accelerating that way for 5 seconds. There's not a good way to measure time. And then I want to know how fast I'm going later. So I'm going to be getting faster and faster, and then over here sometime I'm going to be going another speed, and I'm trying to figure out what that speed is. So I've done step 1, which was draw a picture. What's step 2? Step 2 is knowns and unknowns. Okay? So let's go through these. 30 meters per second, what is that? Well, 30 meters per second we know is a velocity, but when I talk about, so I'm going to say it's a velocity, but I got to be careful because I've got 2 velocities here, right? So if the speed is 30 meters per second, that's what I started with. So I'm going to call that my initial velocity, right, VI. Then it says I undergo an acceleration of 1.2 meters per second squared. So acceleration, 1.2 meters per second squared. For 5 seconds, that's a time. How fast is it going now? So if I want to know how fast it's going now, I'm looking for the final velocity. So I'm going to say VF equals question mark. All right, so let's look at this then. So the equation that we're going to use, since we're actually going to have to use 2 equations, right? So let's look at the equations we had. We know we're going to have to do something with acceleration, and we're also going to have to do something with a VF and a VI. So I'm going to write down these 2 equations because I'm going to use both of them. A equals delta V over T, and delta V equals VF minus VI. Now in this case, I can actually combine both these together. So I'm going to plug in the VF minus VI up here. So delta V is VF minus VI. So I've got acceleration equals VF minus VI over T. And then I can plug in my numbers. I've got 1.2 for A equals the VF I don't know, so I'm just going to write VF, minus VI is 30, divided by time is 5. So that's my plug and chug step. How do I solve this? Remember what I said the last time. We're always going to start, so I chose my equation and I plugged things in, and then the next thing I did was I multiplied by what was on the bottom to cancel it. So in this case, I'm going to multiply by what's on the bottom, which in this case is 5. So if I multiply both sides by 5, on this side the 5's are going to cancel, and then I'm going to get 5 times 1.2 on this side, which is 6. So I'm going to have 6 equals VF minus 30. And then how do I solve that equation? I should be able to solve this by adding 30 to both sides. And I'm left with a VF of 36. Now I can't just say 36 because remember step 5 is to give me an answer, but to give me an answer with units. What are the units of velocity? The units of velocity are meters per second. So this should be 36 meters per second should be your final velocity. All right, that does it for the notes. If you are remote today, there's an additional video you need to watch. But that's what we've got today for the notes.